Okay, so we will start with the last part from linear transformations. So we will talk about one-to-one and onto linear transformations, and also the transition matrices as well for linear transformation and so on. So let's get started. All right, so this is the last part, hopefully, from the linear transformation. So one-to-one and onto linear transformations.
I can't see what you're writing.
Oh my goodness. Wait, sorry. Share content. Ouch. Okay, sorry about that. I forgot to formations. Okay. Ouch. So one-to-one and onto linear transformations. All right, so let's start with the definition. Can you see? Can you see now?
Yes, sir.
All right. So definition: a function t from one vector space to another vector space. Let's say we have t from V to W is said to be one-to-one, or sometimes we call this injective, but anyway, one-to-one, let's call it like this, when the preimage of every, let's say, W in the range consists of a single vector. And I will explain immediately what this means. Right? In other words, T is said to be one-to-one. Let's write it with one-to-one. Or sometimes we call, okay, injective. So keep in mind also this word. If and only if for all U and V in V with T of U equals T of V implies U equals V, right? So that's basically what you need to know. This is the injective or one-to-one. This is what it means for a linear transformation to be injective or one-to-one. In fact, we will see some things, some sufficient conditions. You will see in examples when a linear transformation is one-to-one and when it is not. And now I want to veer towards the following theorem. Which says the following: let T be again a linear transformation from V to W then T is one-to-one and T is one-to-one. This will be a very important if and only if the kernel of T consists of the of one element, and that element is the null element. That's what you need to know, and we will use this in applications. Keep this in mind, right? So this is a very important theorem. Like I said, you will see that this will be used in applications. And now let's see some examples. So examples And let me start with the first one. Let's say the linear transformation let's say T from the set of m by n matrices, m, let me write this m in this way so that I would not confuse you, mn with real entries, and this will be into mnm, so the set of n by n matrices. And of course, as you can imagine, this will be given the map that turns swap the two will be the transpose, right? T of A is the transpose. This linear transformation is one-to-one because its kernel consists of the zero element, consists of only and the m by n zero matrix, right? So you look at the kernel, the kernel of A, in our case, it's are those elements for which T of A equals 0. But T of A is A transpose is the null matrix. Well, this happens only if A is the null matrix, so it's quite clear. The second trivial example is the zero transformation. The zero transformation let's take T from R3 to R3, is not, and I want you to pay attention here, is not one-to-one because its kernel consists of all of R3. Consists so wait, its kernel is all of, okay, is all of R3. So it's the zero transformation. Basically, it's just zero, so you can put anything there. Anyway, now let me give you the following definition. Yeah, don't worry, John. You can, yeah. I'll be, you can, guys, come in, come out as whenever you want. It's not. A function T from V to W is said to be onto. Now we want it to be onto when every element in W has a pre-image in V. Keep this in mind. Well, every element in W has a pre-image in V. This is very important. In other words, T is onto, let me see how, or sometimes it's called surjective. So injective is one-to-one, surjective is onto. This is onto, okay. If and only if, plain and simple, if and only if, the rank of T the rank of the linear transformation, and we have seen what that is nothing else than the dimension of the W. Pretty simple, plain and simple. And now similarly, we'll have the following theorem. Again, let me consider a linear transformation. Let T from V to W be a linear transformation with vector spaces V and W, and this will be an important condition, both of dimension n. Of dimension n. Okay. Well, something happens here. Then T is 1-to-1. If and only if T is onto. Surprisingly, they're equivalent. If we have a linear transformation, I want you to pay attention to this theorem. If I have a T, a linear transformation from these two vector spaces, V and W, and both of them, they have the same dimension, this is important, then you prove one of them, you prove the other, and the other way around. So T is onto, then it follows that T is 1-to-1 or the other way around, right? All right, so this is what I think these are the most important things that you need to know for 1-to-1 and onto linear transformations. And now I want to go a little bit further to talk about, because all these notions will be put together at some point when we'll try to find out and talk about if a linear transformation is invertible or not, or maybe even more, if it is invertible, to try to find the inverse of a linear transformation, just like we found the inverse of a matrix, provided that that matrix is invertible. So we want to do basically the same thing for linear transformations. But before we go and do this, let me talk about isomorphism of vector spaces. We want to see what this is all about. So definition: a linear transformation T from V to W that is 1-to-1 and onto, as I told you, I want to put all of these two notions together. A linear transformation that is 1-to-1 and onto is called an isomorphism. That's what we call an isomorphism. Moreover, if V and W are vector spaces that such that there exists an isomorphism okay, from V to W, then we say that V and W are isomorphic. Then V and W are isomorphic to each other. Sometimes we even have a way to write this, and we're going to write something like this. Anyway, some people prefer it like this. Some people, so V is isomorphic to W. Sometimes they put even 2 here, but anyway, it doesn't really matter. They're kind of the same, but we will see examples of things that are isomorphic immediately. Right? For examples. Let's see. R4. So imagine taking vectors in R4 and, well, imagine taking this vector space R4, and this will be isomorphic to the set of matrices M41 or even M22 are isomorphic to each other. In fact, we'll see maps which will send elements from R4 all the way to M22, for example. There will be a linear transformation that will take elements, a linear transformation that it is one-to-one and onto, that will take elements from R4 and they will it will be sent into M22, for example. All right, we'll go there and we'll see some problems how to do this. But before I even go that route, I want to discuss another thing, and which I haven't done yet. And also, this is important as well. The question is, when I do have a linear transformation, right? Suppose I have a linear transformation that goes from R3 to R3, for example, and it's given in a certain way. Is there a way for me to associate a matrix? Does this linear transformation can be represented for as a matrix, for example? So matrices for linear transformations. Okay. The question is, and I want to be clearer about what I just said earlier. Maybe I was a bit vague. And now I want to be specific. Which representation is better? And I'm going to represent a linear transformation 2 ways. Let me just say I have one from T3 to T3, which is given by Tx1, x2, x3. So I take a vector in R3, and this will be sent to another vector in R3, let's say 2x1 plus x2 minus x3. The first component, negative x1 plus 3x2 minus 2x3. And then the last component, 3x2 plus 4x3, let's say. Okay, so I have this representation, right? As you can see, T sends from R3 to R3. So keep in mind, so I have this one, right? And now I want to see what happens if I write it in a different way, or this one or this one. T of x, which is ax, and I can represent it in this way. 2, 1, negative 1, negative 1, 3, negative 2, 0, 3, 4, right? And then I times this vector, x1, x2, x3. Well, that is the question. Which one is better? The one given directly or the one in the matrix form? Well, you will see that sometimes it's better to represent it in a matrix form, and I'll explain immediately why. The key how should I phrase it, to representing a linear transformation T from V to W by a matrix is to determine how it will act on a basis for V. This is important. This is why it's important to represent linear transformations in their matrix form. Once we know the image of every vector in the basis, okay? So once we know the image of every vector in the basis, okay, we can use the properties of a linear transformation okay, to determine T of V for any V in V. Okay. And now, so this is what you need to know. And now we'll do the following. Let us recall that that the standard basis for Rn is the following. B will consist of these vectors, E1, E2, all the way to En, right? And this will be, like I said, these vectors, 1, 0, 0, 0, 1, 0, and we go all the way to 0, 0, all the way to 1, right? So this is the standard basis in Rn, right? And now we have the following theorem. I will consider this time a linear transformation from Rn to Rm. So let T be from Rn to Rm be a linear transformation, such that for the standard basis, EI for Rn, we have the following. T of we apply this linear transformation to the first vector. T of E1 will be sent into these elements. A11, A21, AM1. As you can see, this will be the column of the matrix. Then TE2 will be A12, A22, AM2. And we go all the way, TEN, T of EN will be this vector A1N, A2N, and we go all the way to AMN. Okay, so we know this, and guess what will happen? Then well, as you might expect, the M by N matrix, whose N columns correspond to T of EN, EI, let's say. And this matrix clearly is given by A is, as you can see, I can just put the columns here, so let me do it. A11, A21, AM1, A12, A22, all the way to AM2. And this goes to A1N, A2N, AMN. Right? This matrix, so the M by N matrix whose N columns correspond to T of EI, which is this one, is such that T of V is AV for all V in Rn. In other words, the matrix A, is called the standard matrix for T. That's the standard matrix for my linear transformation T. In other words, if I would go back to my example, is it clear, Liliana?
Yes.
Okay. Then now, if I go back to my example, you see here, I'm just doing this. So that's the matrix representation for this, the standard matrix for this linear representation, right? If you look at it, that's the standard matrix. Anyway, let's see an example, because I want to illustrate this through an example how this will work. But keep this in mind, this is a very important theorem. And now let's see an example. Find the standard matrix for, and I'm going to take this linear transformation from T, this linear transformation T from R3 to R2. And this T of, let's say, T of X, Y, Z will be X minus 2Y and 2X plus Y, let's say. And I want to find the standard matrix. So how we should approach this? Let's think. Well, the only thing that comes into your mind would be, okay, let's see. So I have a linear transformation from R3 to R2. It looks the way it looks, as you can see. So it takes a vector in R3 and it sends it to a vector in R2 through this map here, T of X, Y, Z. And now I want to write the standard matrix for this linear transformation. So what should I do? If you look back at the theorem, look here, right? I have to see, and look at the first part of the theorem, which is important. I want to see how this linear transformation will behave towards the vectors in the standard basis, right? So in other words, I would like to see the image of these vectors in the standard basis through T, right? Just look at the theorem. It's from Rm to Rm, and you see it sends these elements in the standard basis, these EIs, they will be sent into some columns there. Then I will take those columns and I will just form the matrix, right? So let's do it. So we begin by finding the images of E1, E2, E3. Pay attention here, I have three vectors in the standard basis because I'm looking at R3. So my linear transformation is defined from R3 to R2. All right, okay. So I need to look at this, T of E1. T of E1, keep in mind that, okay, first of all, T of E1 will be T of 1, 0, 0, right? This is my vector E1, which will give us what? Can you tell me what this is?
1 and 2.
1 and 2, correct. So we can write a T of E1 as, and let's write it as a column vector because we will form the matrix is 1, 2. All right, let's see. T of E2 will be T of 0, 1, 0, which will give me what?
-1.
Look, 0. So y would be 0 is y would be 1. So it's -2, 1. Right? Are you convinced?
Yes.
-2, 1. All right. And now let's see the last one, T of E3, T of 0, 0, 1, which will give us what?
0, 0.
0, 0. So T of E3 is 0, 0. And now guess what? Based on our theorem, we can write A. So how should I say? The standard matrix for T, the standard matrix for T for my linear transformation T is given by, I'm going to write it just like in the way like the theorem says, right? It says, okay, so it will be this matrix, T of E1, T of E2, T of E3, which will be equal to, in our case, so let's put the columns here. The first one will be 1, 2, -2, 1, and then 0, 0. And this is what? It is a 2 by 3 matrix, which is exactly what we, anyway. This is how we write a matrix in the standard. The standard matrix, this is how we find a standard matrix for a linear transformation. Okay, well, let me mention something here. A little practice will enable us to determine the standard matrix for a linear transformation, right? But, and let me give you an example. Let me go back to, so for example, to find the standard matrix for the linear transformation, say TTU of x1, x2, x3, which is x1 minus 2x2 plus 5x3. Let's say 2x1 plus 3x3 and 4x1 plus x2 minus x3. So to find the standard matrix for this linear transformation, we use the coefficients of x1, x2, and x3 to form the rows of A as shown below. So in other words, we will have the following. So A will be, well, it's quite clear. I don't, 1, negative 2, 5, 2, 0, 3, 4, 1, negative 1, right? Right, it's quite clear. So you just look at the coefficients of the first component, and then you'll put them on the first row, and that's it. All right, let me take some other example, just an easy example. Maybe I shouldn't waste my time with this, but anyway, let's just do it. I want to find the standard matrix for another linear transformation. Let's say I'll take T from R2 to R2, and this guy projects each point in R2 onto the x-axis as shown below. So let's draw a picture here. This is the y axis. Then this guy here like I said, what will be projected on the x-axis. So this will be x0, and this map will be T of x, y is x0, right? Well, guess what? Well, this is a linear transformation. So this linear transformation is T from R2 to R2. And the only difference when you project on the x-axis is that the second component will be 0. In other words, T of x, y will be x0. Clearly, the standard matrix for T for T is given by A. So A will be T of 1, 0, right? And T of 0, 1. And it's quite clear that this will be nothing else than just 1, 0, and 0, 0. That's the standard matrix for the projection on the x-axis, which is a linear transformation, right? You just look at the picture. You project on the x-axis, so the second component will be 0. So T of x, y is x0. Okay, now let's veer towards something else, the composition of linear transformations. Before I even talk about you know, I've talked about isomorphisms, but before I even go and talk about the inverse of a linear transformation, I want to talk about the composition of linear transformation. And what is this all about? You will see that the scenario is pretty similar to the one that you know for functions, but this time, instead of those functions from R to R, or I don't know, some intervals that you have learned in pre-calc or calc, whatever. Now we'll deal with the composition of linear transformations. For example, one linear transformation will send you elements from Rn to Rm and so on. Okay, so we want to do this. Just a second here. Okay. The composition T of T1, and this T1 will go from Rn to Rm with T2 going from Rm to Rp, pay attention here, is T of V equals T2 of T1 of V. That's what we call, where V is a vector in Rn, right? Because look, T1 of V, and V will live in the domain of T1, which is Rn, right? This composition is denoted by what? By, I'm going to write it in this way. T is T2 circ T1. This is how you denote it. Or if you want T2 of T1 of V. That's what we mean, right? As you can see, this guy above here is nothing else than just this one here. So either way you write it. We can, and let me just explain it a bit, and then I'll draw a picture. The domain of T is the domain of T1. Moreover, the composition is not defined unless the range of T1 lies within the domain of T2. And let me describe this with a picture. Okay, I'm gonna write, this is, let's say this is Rn, and I'm gonna consider here this element here, this vector here, Rn. This guy here will be, let's say Rm. Again, I'm gonna take an element W here, and this guy here will be Rp. I'm going to take this element, let's say U here. You see, I have 3 elements and they live in their own world. And I want to send this guy, I want to send it to this guy here. So this will be sent through T1, the first map. Imagine like there are 3 islands here, and the map is like a plane. So I'm sending one person to from the first island to the second island, and of course the map T1 will be a plane. And then I'm going to take another plane from the second island to the third island. Let's say you see, like having layovers. In fact, I want to go from the third island from the first island, sorry, to the third island. But I can do it 2 ways. I can go directly. So, okay, so this is T2. And now I can go directly, like here, like this. This is just T. So instead of having layovers, landing on the second island through the first plane, and then taking the second flight to go on from the second island to go to the third island, I can just go directly. And that's exactly what the composition is all about, right? Anyway, I hope this picture is clear enough. That's exactly what it is. That's what this picture, I think, describes the best the composition of linear transformations. And now we'll have the following theorem. In fact, this next theorem emphasizes the usefulness of matrices for representing linear transformations. And let me just say it. Theorem, which again will concern the composition of linear transformations. Okay. So we'll consider let T1 from Rn to Rm and T2 from Rm to Rp be linear transformations with standard matrices A1 and A2. Okay, the composition T, which goes from Rn to Rp, defined by T of V will be T2 of T1 of V, right, is a linear transformation. So the composition, in other words, of 2 linear transformation is a linear transformation, right? Moreover, and now we want to see how this, the standard matrix for this composition of these 2 linear transformations would look like. Moreover, the standard matrix A for T is the matrix product. A, which will be A2 times A1. That's it. And now let me give you an example. So example, to see how this will look like. Oh my goodness. Okay. Let me just shut down some, mute some conversations here. All my friends, my sister, my mother, whatever, decided to. Anyway. And now let's see, let's consider T1 and T2 be linear transformations from R3 into R3, right? Such that T1 of xyz is 2x plus y, 0, x plus z. And now let's look at T2. Okay, I'm going to write it here. T2 of xyz. As you can see, both of them are defined from R3 to R3. So T2 of xyz will be x minus y, z and y. Ooh. Pay attention here. And we're asked to find the standard matrices for the compositions and I'll have two compositions here. As you can see, I can look at T1 composed with T2, but also T1 composed with T2. So let's say T will be T2 circ T1 and T prime, and by the way, this is not the derivative anyway, is T1 circ T2. Okay, I want you to look at it for a moment. And well, as you can see, this is pretty straightforward. What we need to do here is just to apply basically the above theorem. As you can see, just look at the above theorem, the composition of linear transformation. So in other words, I need to do what? To find the standard matrices for the two compositions. So what do I need to find? Can you tell me? By just looking at the theorem. Is my question clear? So, okay, let's look again. First, let's look at the theorem. I have two linear transformations, and to both of them, I will associate these standard matrices, A1 and A2. First, let's write the standard matrices. First, let's write the standard matrices for T1 and T2. Okay, let's do it. Let's see. For T1, let's denote this by A1. Will be what? If you look at T1 of xyz is 2x plus y, so it will be what? 2, 1, 0. On the first row, on the second row, you'll put what? You have 0, 0, 0, right? And the last one will be 1, 0, 1. And for the second linear transformation will be what? Let's look at the second linear transformation. So I have only x and y, so I'll have what? 1, negative 1. I don't have any z, so I'll put 0, right? All right, let's look again. The second one I have, it has only z, so the rest are 0, so it will be 0, 0, and the coefficient of z is 1. And the last one has only y, and the coefficient is 1, so I'll have 0, 1, 0. So these are the standard matrices for my linear transformations, right? This is for T1, and this is for T2. Is it clear?
Yes.
Okay. And now let's look at the theorem by the previous theorem. I'm interested, look here, and for the standard matrices for the first composition. So let's see. The standard matrix for this guy here, for T equals T2 composed with T1. So based on the theorem, and let's go back to the theorem. T2, and this is T, okay. This is here T2, circ T1 of V. Right, let me put it like this. So the standard matrix for T will be what based on the theorem? And look what it says. The standard matrix for A for T will be the product. So in my case, for T2 composed with T1, what is the standard matrix? Let's say A will be what based on the theorem? Will be the product, A2 times A1. Just look here. See, the product, A2, A1. For T2 composed with T1, it will be A2 times A1. So it will be the product. And let's write them. Let's write the product. So it will be 1, negative 1, 0, 0, 0, 1, 0, 1, 0. And this guy will be, so the second one is, no, it's the first one, sorry. 2, 1, 0, 0, 0, 0, 1, 0, 1. Oh my, and now we have to multiply these two matrices, whatever, and this will give us, so, wait, so 2, okay, so it will be 2, 0, 1, 2, 1, 0, sorry. 1, 0, 1. And the last one will be, no, the last one is just zeros. Okay. And now the same thing, the standard matrix for this composition, this time we'll have T1 composed with T2 will be what? Again, let's write the matrix. So it will be, this time will be A1, A2, which is, again, 2, 1, 0, 0, 0, 0, 1, 0, 1. And we're going to multiply this by 1, negative 1, 0, 0, 0, 1, 0, 1, 0, which will be equal to, oh my, and here we go again. Let's multiply these two matrices. So 2, so it will be 2, negative 2, 0, then, okay, 0, 0, 0. One, 0, 0. Anyway, that's pretty much it. Right? Is it clear? So it's just the multiplication, and that's it. It's not a. And now, since we've talked about, and now I'm bringing towards something else, and hopefully I get to finish what I have to say, because I would like to talk about the inverse of a linear transformation, and this will be very important. So the inverse of a linear transformation of a linear transformation. So definition. If, let's say I have T1 from Rn to Rm and T2 from Rn to Rn. Wait, they're from Rn. What am I saying here? Okay, our linear transformations such that for every V in Rn, we have that T2 of T1 of V is V. Not just the composition, the composition of T2 and T1 is actually V, and the other way around happens. T1 of T2 of V is V, so is the identity. Then we can say that then the inverse of T1 wait, how should I say? Then is T2, right? And moreover, T1 is said to be invertible. So I can say that if this happens here, this and this, so you compose T1 with T2 will give you the identity, and T2 with T1 will give you again the identity. Then you can say that T1 is invertible, and moreover you can say that T2 is the inverse of T1, and the other way around you can say that T1 is the inverse of T2, and so on, right? So that's the definition. And now let me point out the remark here. This is very important. Remark. Note that not every linear transformation has an inverse. If the transformation T1 is invertible, wait, so if the transformation T1 is invertible, however, then the inverse is unique. This is an important thing to know. So there is only one. The inverse is unique and is denoted by T1 to the negative 1. This is how, okay, this is how are we going to denote the inverses, by T1 to the negative 1. Right, just like the inverse of a real function. This can be thought by just doing that, right? Okay. And now let me give you the following theorem. And after that, we'll do an example. So theorem. And we'll see how this theorem relates the fact that the linear transformation is invertible if we know that we know that it is an isomorphism, and if we prove that T is invertible, then how can we find the standard matrix for the inverse of the linear transformation? Anyway, so this following theorem will address exactly this issue. So existence of an inverse transformation. Inverse transformation. Let us consider T from Rn to Rn. As you can see, both have to be the same of dimension, and you'll immediately see why. Be a linear transformation with the standard matrix A. Then the conditions listed below are equivalent. Okay. The first one, T is invertible. The second one, T is an isomorphism. The third one, A is invertible. Right? And if T is invertible, with standard matrix A, then the standard matrix for T inverse, guess what, is nothing else, is A inverse. So I want you to look at the theorem, look what it says. It's quite clear. Basically, it says that T is invertible if and only if it's an isomorphism. And now let's, okay, look at it a bit. And now we would like to see this theorem at work for the following example, which is quite pretty straightforward. So example. So this example basically will concern finding the inverse of a linear transformation. So consider the linear transformation T from R3 to R3 defined by T of x1, x2, x3 is, okay, let's see, 2x1 plus 3x2 plus x3, 3x1 plus 3x2 plus x3. And now let's take, oh man, I hope I won't take 2x1 plus 4x2 plus x3. I hope I'm not going to deal with the matrix that's not invertible anyway. Show that, but probably is not going to be the case. T is invertible. And find its inverse. So again, we want to use this based on the previous theorem. I want you to look again at the previous theorem, look at it. In other words, to show that it's invertible, we need to do what? Can you tell me? To put it plain and simple. Look at the conditions, they're equivalent. So my linear transformation is invertible if and only if what? What happens? If and only if the matrix, the standard matrix associated to that linear transformation is invertible. It's plain, it's pretty simple, right? So the standard matrix for T is given by let's say A will be this matrix, 2, 3, 1. So it's a 3 by 3 matrix. Let's keep that in mind because my linear transformation goes from R3 to R3. So 2, 3, 1, 3, 3, 1, 2, 4, 1. Well, the only thing you need to find is the inverse of this linear transformation. So I'll leave it to you as an exercise. One can prove that the determinant of this is not 0. So therefore, so A is invertible, right? And of course, and the inverse exists. And I will leave it to you as an exercise to compute the inverse. In fact, I think I have it somewhere here in my notes. Let me see. I think I've done this computation. Let me see. Okay. In fact, one can show that A inverse. Well, again, you can use that. You can do it in many, many ways, whatever. And if I'm not mistaken, then I'll leave it to you as an exercise to show that A inverse is, let me look. Oh my. So it will be -1, 1, 0, -1, 0, 1, and 6, -2, and -3. Okay, I'll leave it to you as an exercise to show that. That's it. So T is invertible. And the standard matrix for T inverse is A inverse. Right? That's it. Now let me point out a remark. It's almost a remark. Well, you can use the standard matrix for the inverse. So using the standard matrix for the inverse, one can find T minus 1, the inverse, by computing the image of an arbitrary vector x, x1, x2, x3. And now we have the following, just like you have been used. So we have A inverse of x. You can just put the inverse here that we just computed, so negative 1, 1, 0. The second one was negative 1, 0, 1. And the third one was 6, negative 2, and negative 3. And you can multiply this by this vector, x1, x2, and x3. And this will give us, if you do the multiplication, and this is quite easy to see, this is negative x1 plus x2. The second one will be negative x1 plus x3. 6x1 minus 2x2 minus 3x3. Or you can say that, or T inverse of x1, x2, x3. So if we want to write the inverse of the linear transformation, we can write it like this. So it's negative x1 plus x2, negative x1 plus x3, 6x1 minus 2x2 minus 3x3. That's it. So end of story for this. All right, there is one other thing I want to mention. I know I'm out of time here, but I would like to mention this. And well, if you don't like to stay, I don't want to do another video. In fact, probably I'll do another video, but with similar matrices, because I need that for my eigenvalues. Anyway, there's a lot of material, but hopefully I'll be done with this today. But I want to mention one more thing. And this one more thing that I want to mention is the following. Let me think. So what happens when we deal with non-standard basis and general vector spaces? And this is important here. I want to mention this. Anyway, but before I go into this, is it clear what I just did? I went a bit faster, but is it clear?
Yeah, his last part's pretty straightforward, I would say.
It's very straightforward, right? In other words, it's just like using the theorem. It's just basically look at the theorem. That's what you need to do. It's just like finding the inverse of the matrix, of the standard matrix is the same as finding the inverse of the linear transformation. That's, I might put some examples where I will ask you something like, show that this is an isomorphism. You'll be like, oh my God, how do I show that this is an isomorphism? Then you'll think like, wait a second, there was this theorem which says that an isomorphism, that linear transformation is an isomorphism if and only if is invertible. But what it means for my linear transformation to be invertible? Well, it means that the standard matrix associated to it is invertible. Oh, okay, so it's just about matrices at the end of the day. Anyway, it's pretty straightforward, but I'll do more examples of the review session. And now I want to talk about something, I think it will take 10, 15 minutes at most, non-standard, but I want to mention this as well, basis. Okay, plural is basis, and general vector spaces. And now, what is this all about? Well, in this case, I will consider a more general problem of finding a matrix for a linear transformation. So the thing is that we want to find a matrix for a linear transformation T, let's say from vector space V to another vector space W, where, and in this case, I'll consider two bases in each vector space. One B and B prime are ordered bases for V and W, right? Okay, and now let me go back to what we said about representing this through the coordinate matrix. So recall that the coordinate matrix of V, okay, so the coordinate matrix of V relative to B, to the basis B, is denoted by this V, by VB, right? Okay. And now, if we want to represent the linear transformation T, we're going to do the following. Multiply the matrix A, right, which is the standard matrix for my linear transformation T, by a coordinate matrix relative to B. To obtain a coordinate matrix relative to the basis B prime. Relative to B prime. That is T of V, in fact, let me write it like this, that is T of V So this will be relative to the basis B prime will be A times the vector V in relative to basis B. So this is what we do. And we say that the matrix A is called let me change the color. Let me write with pink. It's called the matrix of T relative to the basis of B and B prime. Okay. All right. This is what you need to know, this thing right here. And now let me just say it the way it is, right? And now instead, I'm not going to have the standard basis in Rn. So I'm just modifying, instead of Rn, I have this linear transformation that goes from one vector space V to the another vector space. And now I'm going to consider a basis. In other words, we'll have something similar. So we'll have the following transformation. The transformation matrix for non-standard basis. Let V and W be finite dimensional this is important vector spaces with basis B and B prime, where, okay, let's say B will consist of these vectors, V1, V2, all the way to Vn, right? And now, if T defined from P to W is a linear transformation, such that, again, we will have a similar condition, but this time instead of the vectors, last time we had those vectors V1, V2, Vn were E1, E2, En, which is the standard basis in Rn. So this is just a base in V. So if this is a linear transformation such that T of V1 relative to the basis B prime is A11, A21, and we go all the way to AM1. Let's write another one. T of V2 relative to B prime is A12, 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 A22, AM2, and we're going all the way to T of Vn will be A1n, A2n, AMn. Then guess what? Then the m by n matrix whose n columns correspond to TVI relative to B prime is given by the following. So A will be, as you can imagine, I'm just going to put these as columns. So it will be A11, A21, AM1. A12, A22, AM2, and we go always basically the same thing as A1N, A2N, AMN, right? Is such that T of V is relative to B prime is A times V relative to B. For every V in the vector space V. Oh my, it's kind of long, but I think it's easy to see. And okay, let me just give you an example because I want to find a matrix relative to non-standard basis, just like I illustrated in this here. But anyway, it's actually, the writing is more difficult than just to explain it. It will be easier to explain. And I think I'll stop here after this example. So this example, like I said, will concern finding the matrix relative to a non-standard basis. And let me think of one. So this T, I think I have somewhere here in my notes. I found one. I don't want to think of one. So let me see. Okay, let me take a simple one from R2 to R2. Be a linear transformation. Okay, defined by T of x1, x2 is x1 plus x2 and 2x1 minus x2. Okay, find the matrix for T relative to the basis B will consist of these vectors, let's say 1, 2, and negative 1, 1. And B prime, you see this time I'm not finding the matrix for the linear transformation T relative to the standard basis. So B prime will consist again of these vectors, 1, 0, and 0, 1. Haha, but actually this is, look. Okay, so this is the vector V1, this is V2, this is W1, in fact it's E1, but anyway, that's denoted by W1 so that we can fit everything into the, we can fit the notations perfectly into the picture. Okay, right, so this is what we need to find. And now let's look at the theorem. You see, what I need to find is just to evaluate these vectors in the standard basis B. So that's what we're going to do. So we have, by the definition of T, we have that T of V1 will be T of 1, 2, which will be what? Can you tell me? Will be what? What is T of V1? You just replace it there, right? So x1 will play for 1, x2 will play for 2. So this will be, it will give us what? 1 plus 2 is 3, and the second one is 1, 2. So 3, 0. Which will be, I can express this as a linear combination of the vectors in B prime, which will be 3 times W1 plus 0 times W2. Nice. The same thing will happen for V2, so this will be T of negative 1, 1, which will give us what? Will be 0 and negative 3, which again, this can be expressed as 0 times W1 plus negative 3 times W2. Perfect. That's exactly what I want. Therefore, the coordinate matrices for T of V1 and T of V2 relative to B prime are T of V1, which is, we'll put this 3, 0 as a column, and T of V2, which will be 0, negative 3. So now we form the matrix T relative to B and B prime by using these coordinate matrix, these two coordinate matrices. And as columns. And we have what? Well, let's write it. A will be 3, 0, 0, negative 3. And that's it. Okay, guys, I think I'm going to stop here. I went a little bit too much, 20 minutes, 21 minutes over time. Well, thank you very much.